Now I can proceed with my slides. So I will take now the point of view of inference, and of course this will overlap partly with Jessica presented, and also Janaina, with a slightly different flavor. So first of all, the term inference. I see MVPA, multivariate pattern analysis, as an inference procedure. First of all, because of the inference mapping that people do when they just probe whether there is information between brain images and some outcome variable y, so it's a way to map information. But there are also other types of inferences performed. Typically, you might want to test some classification rule across data sets, in which case we could consider that as a kind of transfer learning, when you learn to classify on a given data set and apply it to another one. So it's a more powerful generalization. It's transfer learning, and it's another type of inference. And also, I'd like to emphasize that MVPA is a tool of choice to do individual prediction, like in diagnosis problem. When you want to say something about a particular subject, classical statistics are essentially useless, and MVPA becomes very useful. So typically, this unfolds into two questions. Question one, is the information present in the dataset? Yes, no, and this is where classification accuracy typically matters, and you want to compare it to some chance level. And question two is, how is the information represented in brain activity? And then we go more to the pattern analysis, which I will get back to later. So I like to start with the sample size issues, because I think it's so important that we should emphasize it again, and then I will get more to the deeper to the inference question. So there's lots of information in this slide, but I think the main information is on the yellow plot. You see different simulations of classification problems, and you see that essentially the uncertainty on the classification rate decreases with the sample size. So on the left, you've got the sample size from 30 to 1,000, and you see essentially that the uncertainty on the classification score decreases as essentially 1 over square root of n, where n is the number of samples that you have probed. And you can confirm that on NeuroImaging data. We obtain essentially these results, and it can be actually predicted analytically by just looking at a binomial variable. So this means that, of course, it's essentially useless to have small samples. You will have very little information or very little confidence in your classification results. Another way to see that, actually, it's a different point of view. It's not only the decrease of the uncertainty, but also simply the learning curve. You get more accurate information, better information when you sample more subjects. So here I take an example from voxel-based morphometry. Based on the OASIS dataset, we want to predict the age of the subject. So we can predict this pretty accurately. Essentially 80% of the variance of the age information can be captured by the model, but you see how this number increases when you increase the sample size. So we call this a learning curve. So this is for performance, and of course you see that also the uncertainty decreases with increasing n. But now, if we look now at the pattern map used to predict the age from the anatomical data, so you can take now a group of subjects and obtain a pattern map. Okay, but what if you take another group? Well, you obtain a different answer. And, well, it's similar to some extent, but, also different in many regions. And if you do that on 10 different groups of subjects, you obtain 10 different answers. And this becomes a bit worrying. So we've got this kind of instability. So to summarize the situation, you can just take the mean of all these patterns obtained in different groups of subjects and the variance across groups. And to summarize this information, it's just here for educational purpose. So you can have a normalized effect size map by looking at the average across the different groups, divided by the standard deviation across groups. And so you see that in that case, the normalized effect size is pretty small. It's essentially 1 or smaller than 1 in most brain regions, which means that the effects that we see depend highly on the group that we have sampled. Of course, now we redo this kind of thing, but increasing the sample size, and you see how the situation improves and the normalized effect size becomes larger, not because the effect has changed in itself, but because the variability has shrunk hugely by increasing the sample size. So you decrease essentially the uncertainty or the variance on the pattern map that you estimate when you increase the sample size. Okay? So now let's go a bit deeper in inference itself, in MVPA. What people do classically, when they were doing at least brain mapping a few years ago, they were essentially testing marginal associations between brain voxels and some behavioral variables. So you're just essentially testing the correlation, if you want, of the signal in a given voxel and some variables, which is typically embedded in a design matrix. Of course, we are correcting, when we do that, we are correcting for the other possible effects that are modeled in the design matrix, but we are interested in the correlation or the statistical association between the time course of the voxel, say, or the signal in the voxel, and some external variable. And this is typically the SPM framework. That's why I put the SPM logo here. When we do, so I can also call it classic or forward inference, which is mapping see how an effect Y is embedded in brain activity X. If we do the reverse inference, we want to predict Y given X, then what we are actually estimating in terms of pattern is a conditional association. Is an association that remains between the variable Xi and Y once we have removed the effects of other variables. So essentially, it's a conditional correlation, conditional to all other brain regions, all other brain voxels. So I provide a graphical model to interpret this. You've got different variable X, which are interrelated, and they are also associated with an output variable Y. So, by the way, I put a direction on the arrows, but actually there should be the inference that we do is not directed. So actually it should be a bilateral arrow. The question is, given all the other variables, can we say that there is an association between, say, X2 and Y? Okay? And of course, you see that this problem is very hard because we are conditioning on a huge number of variables. So this makes the inference difficult and ill-posed. So first of all, it will depend on the procedure that you use. For instance, if you want, so I take the celebrated XB dataset once again, and you want to characterize the response to faces. You could just classify images acquired when the subject views a face versus images acquired during rest. And then you will obtain a first classifier, which will, for instance, outline the visual regions. Now, if you do a multi-class classification where you compare response to face to all possible other visual categories, there are 8 categories in this dataset, then you obtain a different map. So this is an example of the particular choice that you can do to obtain a pattern. So you could do 1 versus all categories or 1 versus 1 if you want to compare face to rest or places or etc. Depends, of course, on the classifier used, on the cross-validation procedure used, on the hyperparameters that you choose for your classifier, on the loss function. So it's a bit worrying. But I would like to emphasize here, and Janaina also already gave the point earlier, that this is not different from the situation where you are doing univariate inference. For instance, if you take the same data set, the HAXB one, and you want to map the regions that are responsive to faces, you could do a face versus rest contrast, in which case you would obtain the map that I show here. But you could also do look at the activation of faces to faces versus the average of all other categories, so a linear contrast of face versus others, in which case the map would be different. A bit more specific probably, or even better, you might want to do a conjunction. You would like to have the region that respond to faces, more to faces than to any other categories, places, etc., visual objects. The only issue now with the conjunction is that you find nothing positive because it becomes more and more conservative. So we have the same situation with classical univariate inference. The answer depends on the way you ask the question. So the point here is that you should document in a publication, should really be precise on what was actually tested in your classification procedure. But it is also true that with reverse inference, I told you that computing conditional associations was more difficult. It's ill-posed. It's an ill-posed inverse problem. There are lots of solutions, and the point was made by Ana Luisa. Depending on the prior that you use on your solution, whether the map should be dense, in the 3 examples above. So this is still the same problem, but solved with different solvers. Some of them assume that the weight maps should be dense, the 3 on the top. The 2 below have a sparse prior which is regularized by an L1 norm on the coefficients. And the 2 below again are with some structured sparsity that imposes sparsity but with some smoothness in the images, so with total variation regularization, or the so-called GraphNet method. And essentially all these methods have similar accuracy. There might be small differences, but usually they are not significant. And these are equally valid solution of the inverse problem, just because since it is ill-posed, we need to choose between this solution, or at least it's hard to conclude anything on the involvement or not of many of the voxels in the map. And actually we can do simulations to show that. For instance, if you simulate a true pattern with positive and negatively associated regions, and you just sample data by varying the noise, it's just simulation. Just with 3 different noise realizations, you can have relatively different solutions with sparse and non-sparse methods. So this instability is related to the ill-posedness of this type of inference. And actually, we can even have create cases where we will estimate the patterns quite poorly. In particular, when you have a noise with a lot of structure, for instance, a very smooth noise. You can see that the noise is smooth, for instance, because the T-map itself is very smooth, as you can see here. And typically, the pattern estimated is a bit artifacted by this noise. For instance, in the red square here, you obtain blue voxels around, because essentially here the decoder learns the noise on the surrounding voxels to clean the signal in the red voxels. So essentially there is a ringing artifact created by the classifier in estimating the pattern. And the point here is that there is a very strong covariance in the noise, and this covariance corrupts the pattern that you estimate. And even if you use classifiers with, which induce some regularization, like some local smoothness on the solution, you cannot truly deal with the problem. You still have some artifacts in the estimated pattern. Of course, if we change now the simulation and the signal is smoother, I actually smoothed the true pattern, and then it becomes now smoother than the noise, so there is more structure in the true signal than in the noise, then we obtain a good recovery of the patterns using our estimators. This means that in real data, when you have some structured noise, like induced by artifacts, motion, etc., then this will have a bias on the map, which is hard to predict. So far it was mostly bad news. I'd like to give some good news now. We are working on this instability. Of course, it's hard to fight against structured artifacts, but we can partly solve instability problems. And to do that, we can use a solution based on ensembling or bagging IDs, which I call robust solutions. The idea, for instance, is not to estimate your model only once on the data. You can first estimate the model not on voxels, but on clusters in the image. It will make your model already more stable and more reliable. And then you average solutions obtained for different clusterings. So we call this solution the frame estimator for fast regularized ensembles of models. And what we have shown in a recent paper is that this so-called frame estimator, if you compare it to classical state-of-the-art estimators, in terms of accuracy, it's not that much better. It's actually similar to the other models. But the stability of the weights obtained by repeating the experiment on different splits of the data set is much higher. So the ensembling of different models will typically stabilize the solution. And still, the computation time is lower than, for instance, the expensive total variation plus L1 estimator that we provide in NILEARN. So it's a good compromise in terms of having high stability, being not too expensive, and having good performance. And also, it has good properties with respect to the learning curve. If the learning curve is obtained by changing the size of the training data set, and you see that with little data to train, the pattern that you learn will be closer to the pattern obtained with all the data. So it's also a good property, a good stability property. So overall, to summarize this, and typically having an SVM method, like a SVM with L2 regularization, a non-sparse SVM, would give you a certain map. The good point is that it's very cheap. You can get it very quickly. It's not very stable. It's okay. If you take an optimizer like total variation plus L1 regularizer, which is available as under SpaceNet name in NILEARN, it will give typically a more structured solution, which I call nice. But this is very costly and not very stable, while the frame solution is well structured. It's quite stable and affordable. So it's not in NILEARN yet. I'm sorry for that. We will add it in the next months. And just to follow up on this, to give you an idea of ongoing research on this topic, we're also investigating whether we could have statistical significance on the pattern. Have some, so actually test the conditional association of voxel information with output variable. And for this, we are revisiting IDs that have been set up in the domain of genetics, where similar problems occur. And people have proposed some solution to obtain p-values in high-dimensional linear regression, and also a strategy based on the so-called knockoff approach. And so to adapt it to functional imaging, we add a clustering step, as you have already seen, because it makes the result more stable and more usable for us. And then, once again, we aggregate solution to mitigate the impact of the clustering choice. So here is the image of the method. So the workflow is to cluster the data and run an estimator that will give you the significance of each cluster in the model. You do that for several bootstrap replications, and you average these models. Essentially, you obtain an ensembled p-values. For instance, on the AXB problem, so you obtain different solutions for each clustering, but when you ensemble the model, you obtain something which is pretty nice with PPA, the symmetric PPA that are involved in the classification of place images, face versus place images, so negative in this classification model. Or here for the OASIS dataset to predict age based on gray matter density. It's quite conservative, I would say. So overall, regarding inference, so sorry, this thing is, we're working on it. We have a first publication. It's not ready for public consumption. We need to test it more, but I think it's a very promising tool. So inference in MVPA, you've heard it many times this morning. It should be done with caution. It depends on the modeling choice. It depends on the priors that you put on your model. This means that you need to explain what prior you choose and why you choose them. Conditional associations are hard to quantify because of the dimensionality of the data. And in any case, we should not confuse conditional inference with marginal inference. And this is improving with modern tools like the ensembling or aggregation methods that make the results more robust. To finish, I would like to talk a bit more about functional specificity. So once again, remember that when you have a problem where you would like to characterize the response to a certain functional category, like response to place images, really the result depends on what you compared it to. So comparing houses to faces, for instance, is different from comparing them with all possible categories. So you will obtain a different solution. And once again, be precise in describing what you compared. So all the classification procedure matters. Another point that I would like to make, and final point, is the question of linear decodability. Quite often I see in publication that people they decode some information with linear classifier, and so they conclude from that the information is encoded linearly in brain activity. And this is not correct. You can decode something linearly that was encoding non-linearly in brain activity. For instance, let's take an example of with a receptive field in the visual cortex with a retinotopy. So assume that the visual field is one-dimensional, and that you've got voxels in, say, in V1 that map this visual field. So I assume that the receptive field size is the same for all voxels. It's not correct, but just for the demo. So this means that a voxel represents, say, 10,000 neurons that respond when there is an object present in the receptive field. For instance, if you put something in the visual field, then this voxel will display activity and maybe the neighboring voxels. Of course, this is a nonlinear encoding of the position information. If you double the x coordinate of the object in the visual field, this will not double the activity of any voxel. It will just change which voxels are active. Now, you can decode this information linearly. Just put a classifier with a kind of a ramp shape where you just weight the classifier according to the position in the visual field that they map. Then you can so decoding will just be a summation of these responses weighted by the bars here. And then from a certain activity in response to this object, we can estimate the position. If I change the position of the object, I can also predict the position. So I can perfectly decode linearly the position of the object, but it was encoded linearly in none of the voxels. So it's time to conclude. Multivariate pattern analysis relies on complex estimators, and I showed you that the results will be typically be unstable under a small perturbation. When I say the results, I mean the pattern map estimated. So interpretation needs caution. Encoding models cannot be falsified. You can just say that the information can be decoded or not. You cannot say much about the encoding model. So you cannot say how the brain encodes information. You can say that the information is there, but as I just showed you on the linear case, it's not decoding linearly doesn't mean that the encoding is linear. And actually, it's not. Obviously, we know that neurons do not respond linearly to position. And also, brain regions involvement is hard to falsify for the reason that I have given. So pattern maps are highly sensitive to model assumptions and structured noise. So be precise in the way you describe your classification experiments. When you do full brain multivariate pattern analysis, you should use fine-tuned priors. So, for instance, the TV plus L1 is a good solution as far as I know. It gives, at least in my experience, relatively interpretable patterns. And novel estimators like model ensembles are more robust. So the tools I present are or will be soon available in the Nylon library, which is a Python library for doing this kind of machine learning task on brain imaging. So classification things and also functional connectivity learning. And it will be demoed on Tuesday at the early afternoon in the open science room. So with this, I would like to acknowledge the contributions of my colleagues and thank you for your attention.
Thank you.